So today we start to talk about linked lists, and this is a very big topic, extensive topic, linked lists. And of course, we won't be able to tell everything about this in a single video, but we want to create a base, and from that base we'll be expanding in the next couple videos and doing some more advanced stuff. So things like how to reverse a list, how to clone a complex list, which are all very popular interview questions. And before we can attempt to solve them, first we need to understand what are the lists and sort of all things related to it. Yeah, so that's what we do today. And besides it being like an important thing for interviews or coding interviews in particular, what is also interesting about lists is that it is quite important, like in DSA in general. Yeah, so it's important and special because it's sits somewhere in the middle between the very basic concepts and the more advanced concepts. And so what do I mean by that? Well, before you can attempt to understand linked lists and how they are implemented, especially if you are trying to implement them using some more modern practices in C++, you have to understand a lot of things, and maybe not master them. If you master them, it's the best for you, but at least understand them to certain degree. And then finally, once you have those many different building blocks, you can create a list yourself. And those are things like, let's say, arrays. Yeah, so of course, first you go to built-in type, which is an array, and you try to understand how it works, and then you can extend it to a list. And with arrays, usually you also work with strings. You have to, of course, also understand functions, even recursive functions. They are also useful here. And in our case, in C++ in particular, of course, it is a general topic which can be implemented in any programming language. But in C++ in particular, there are certain things which are, let's say, maybe more complex or more demanding than in other languages. Yeah, so that's all of the things related to object-oriented programming, which are specific to C++. You also need to understand them, or it's a good opportunity to deeper understand them, on a deeper level. Things like, let's say, constructors. And what are constructors? What are destructors? What type of constructors you have? Move semantics, copy constructors, copy assignment operator, move assignment operator, move constructor, and so on and so forth. Yeah, so there's a lot of things that we'll discuss in greater detail later. I just want to sort of make this background first and highlight how important it is and how many different topics come together into inside linked lists. Yeah, and the other thing besides all that things related to object-oriented programming is, of course, memory management, yeah, which is, again, very important thing for C++. And this will be a thing that will be tested during an interview if you have a topic or if you have a question related to linked lists. And they will try to understand how deeply you understand things like pointers, memory allocation, ownership, and so on and so forth. Yeah, so this is very good way to gather all those different building blocks and sort of revise them and make sure that you understand them really well. And that's what we will do, of course, today and also in the next videos. But before we go into linked lists themselves, first let's discuss another related topic, maybe sort of separately. I'm drawing these lines to separate what will come here from linked lists, and that is an array. So I already mentioned that it's good to know before you start working with linked lists, and we want right now, of course, explain everything related to arrays, just the picture of how arrays work, and this will be the key to understanding or being able to answer why we even need linked lists in the first place. And so when you once you understand arrays, then you will understand their drawbacks, what sort of things they are good for, what sort of things they are not so good for, and then you understand where are the linked lists coming from. And let's draw it like this. So we have two boxes. Those boxes store some data, and a data structure stores data, some values. Could be mixed data in certain cases. In our cases, we have values of the same type. Those all will be integers. Here we put one value, here we put another value, let's say 2. And let's add a bit more boxes to our array and maybe update the values. Add it like this. Here 3 and send it back. Here maybe 7 -1, and maybe this 2 can stay like this. Now we have very beautiful array, and we already said that all of the elements are of the same type. That's very important insight. Same type. Other thing which is important is that we will have concept called indices. And we have 0, 1, 2, 3, 4, 4 and 5. Let's swap them. 5 here, 4 here. And then we have this big concept of memory. What is the memory? What exactly do we mean by memory? We won't go deep into it. For the purpose of this video and understanding the trade-offs between linked lists and arrays, what is important is that there's this universe or this space called memory, which is somewhat mysterious, but we understand certain things about it. And then there is in this memory thing all of our objects, and I don't mean objects as instances of classes, objects like in general, everything that you created that lives inside your program that you created in the code sort of lives within this memory, and it has certain boundaries, and we have to somehow access it. And besides the fact that it allows for storage, so that it has some way that it allows us to store values there, it also has addresses. And those addresses allow us to access the data that is already there. So we have the memory, we have the addresses, and now we store an array inside this memory. And we already drew it like this, that there are boxes all next to each other, contiguous, and all of the same type. So what does it mean? It means that we only need to store the address of the first element. If I store the address of the first element, and inside this memory all other elements live next to each other, and all of them have the same type, meaning we reserve for them the same width, the same amount of that memory, that means that once I have the address for the first element, I can access any other element by multiplying the index by the space that we reserve for them, and we know how much because all of them have the same type. So if I have 100 million elements, I want to access the element on the millionth index. I just multiply the width or the space that was reserved for each of them as the same amount of space, and I add it to the address of the first element, and then I can quickly access the millionth element. On the other hand, if they were not arranged in a such way, and we only had connections between them, like it is in the linked lists situation, then to get to the millionth element, I had to go through each element before. So I had to make like at least million operation before I can access my millionth element. So this is the story behind arrays and where they are very, very fast. So for that particular thing, they are very, very fast, but there are other things for which they are not so fast and for which there shouldn't be used. So if you want right now, you filled your array with data, with values, and you want to just read the value. Then it's very easy, we already discussed it. Maybe you want to update the value. You don't want -1 here. You want, let's say, -99. That's also very easy to do. But what wouldn't be easy to do here? If you wanted to insert something in the middle, and by in the middle, I don't mean like exactly in the middle. In this case, I drew it exactly in the middle, but somewhere in between the ends. So if you want to insert something, how can you do it? There is no space here left for you to insert anything. Well, the only thing that you can do is to move all the values to the boxes next to them. So you would have to move like 2 like this, maybe without the box, 99 like this, and then let's draw it again here, and then finally leave an empty space here, and the new value can come. Let's say new value of 7, or no, 7 we already had. New value of 8. And then the new value can come here, but before it arrived, we had to move all the values after it. And so this, again, if there was a million boxes after that box, that means that we had to do 1 million operation, 1 million transfers just to insert a new value. And this is sort of a thing which bothered a lot of people. So instead of array, they invented a new thing that solves this problem called linked list. And the same goes, of course, for deletion. If now I want to remove the 8, what do I have to do? I cannot leave this box empty because that would break all the assumptions of my array. I have to move everything one by one. Like this. And now this box doesn't belong to the array anymore. And of course, things get more complicated when we introduce dynamic arrays versus static arrays. Here we are more or less discussing the static scenario, so this box actually should be here, but wasn't yet used, so we haven't used the array to the full capacity. But let's not go deep into it. Let's leave it like this. I think should already illustrate for you the big picture of where arrays are fast and where arrays are slow, and why do we bother with linked lists at all. And so now let's create now let's go to the next portion. So finally we arrived at linked lists, and let's add some text. 5, put it here in the middle. We again have boxes. Again, everything works inside memory. Again, there are addresses in memory, and that's how we access our data. But some things stay the same, some things are different. You can already see sort of that, let's make it even bigger, that they are not next to each other. And that may be -3. Okay, so how do we know once we have the first element how to access other elements inside the list? Well, we introduce new concept, arrows or connections or references. and each element stores in the single linked list connection or the reference to the next element. Yeah, so from the first element, I cannot directly access the 10th element, but I can access the next element. And the very last points to nothing, which in C it's called null, or null pointer in C++. And that's how it works. And now, if I want to get, as I said, to the millionth element, I have to go one by one. So I'm not very efficient in this. But if I want to insert something, and I have 1 million elements here, and there's a new box that is coming. Let's copy this one together. And there's a new box that is coming, let's say with 14. I don't have to move all the boxes here. If there are like 1 million elements after and I want to insert it after the first element, I don't care about them. They stay the same in the same place. The only thing that needs to be updated is that first connection. I'll remove this arrow, get rid of it, create a new connection to my new element and a new connection here. And that's it. Okay, so inserting data in between and removing data in between. Here, very slow. Here, very fast. That's the good thing about linked lists. So that is basically the idea behind this, by the way. Let's move it here. And now the next step is to understand, well, what are those arrows and boxes and values, and how are they implemented in the code? In the old C ways, you would do something like this. You would create a struct with 2 elements or 2 fields inside your struct. First, the data, and each value would be, again, of the same type. You can call it value or data or whatever. And then you would, again, put here struct, and you usually call this node. A node here would be the value, the box, and the arrow. To the same type, struct node, but not, you can call it next or pointer or however, but it won't be an instance like this, but it will be a pointer to the next element. And that's the way you would do this. I say you would do this, not what we will do it, because there are better ways right now to do it other than using row pointers. But before we go into it, let's first start with this basic story, since we started from arrays. Then we have row pointer references, and then finally we will achieve more modern ways of solving this issue using smart pointers, and in our case we will use a unique pointer to the next element. Yeah, but basically this is the way you would store something like this, or you would represent it in the code, not store. And because we have here a pointer, now the issue is, how do we create new elements and who owns them? Okay, so, and we talk about this. So what happens here? Well, you would usually create a new elements through malloc in an old C way, and then each element would own the next element. So there is like this recursive ownership. The first element, by the way, is called head. This is the head. To not always refer to it as the first element, they introduce a new name for it, a special name called head. The last element could be called tail, but here let's call only this one head, since we start with single linked lists. Yeah, and each each element creates, like in the old way, through malloc, a new element, but then we have this easy way of reassigning our arrows, but not so easy way of cleaning up the resources, since we had each time we allocate something, then when we remove it, we have to deallocate it. And how, let's say, can I deallocate or remove that element? Well, sorry, not remove. Better way would be to solve how to free the resources reserved by that memory. And the other question, or rather set of questions that we have to answer, is what do we do with all the operations? How do we implement them? So we know that this have to somehow be centered around this idea of the node. And the central question about the node is what do we do with those pointers or arrows and so on? And how do we manage the memory here? What do we do with the ownership? And then, in general, how to implement all the operations. Yeah, so how to insert new data. What is with reading existing data? What is with deletion of elements? And so on and so forth. Yeah, but basically those three questions are the first important ones. Yeah, so we need to create some sort of interface that would allow us to do things like list, and then in the best case, let's say we like in the very best case, we would specify the type by ourselves. But right now, let's start with the simpler case where we predefine that everything, all the data will be stored as integers. We take care of all the other things, the connections and memory management and so on. And then maybe we'll update it to use templates and make our user or the client of the code choose what sort of data he wants to store there. But let's start with just integers inside, and then be able to maybe first, not even like this, just create it, and then add something. Append, maybe let's make it the same way like here, 5, 14, append 7, and so on and so forth. Yeah, so we want to give it to have an option, first of all, to create the list, then to add some elements into it. Then once we add it, we want to read it. Yeah, so either we overload this operator and we are able to read it the same way as for the arrays, like L on index 2. Yeah, what is L on index 2? And be able to print it. And we also should be able to remove it. So either we do it like this, or we do it like this. Or we implement both options, or the next thing that we want to do is to remove. So L remove, let's say, on index 2. Those are all the things that would be nice to have. Now is the time to implement what we discussed about in the code. So we will create a class called list, and this will be our representation of the linked list that we were talking about, with those nodes, pointers, arrows, and so on and so forth, or the operations, inserting data, getting the data out of the list, and so on and so forth. Yeah, so first things first, let's separate the interface into private and public. Yeah, and private are all the things that are internal for the class. And it makes sense definitely in our case, but in general, it's also a useful thing to divide the parts of your class to private and public. And then whenever someone wants to use your class, even if that someone is only within the same code base. He doesn't need to care usually about the private things. Yes, this is the idea behind this. Those are the things that are internal. We don't have to worry about them, and we only deal with objects of the class through their public interface. Yeah, so this is the private internal stuff, and here public things that we expose to the outside world. And this outside world, as I said, could be just within the same code base. And for the private, let's start maybe with the struct that we already had, that we already drew and discussed the node. Yeah? So this is the heart of our list. We need the nodes, and it will have two fields, int data and unique pointer float of the same type and node defined here and then used already as a type of the unique pointer next. And couple things happen here. Multiple things happen here. First of all, why struct? Well, struct have the fields public by default as opposed to class in C++, but this public is not public to the outside world, as we already said. It's within the private. Yeah, so this is an internal thing of the list. Only the list knows about the nodes. The outside world cares about the data and about the indices. Yeah, so someone will say, let's say, append this number, let's say 50 at the end of your list, and then internally you will use the nodes, but to the outside world they don't know that you use the nodes. Yeah, and this is only happens within the list itself. And then unique pointer is very useful here and very in place, since this relationship is ownership. Yeah, so whenever you have ownership, then unique pointer makes sense if this is like a unique ownership. And whenever we have a new node, then there is a previous node which is owning it, and when this node goes out of scope, automatically all other nodes are cleared or freed, and we don't have to define any special distractors or care about freeing memory ourselves. Yeah, so that's another useful thing. Then why it's int here, because we discussed about ints, and I think it's easier to start like this. In general, you would probably use templates and have like some template and type T, which the user can provide. But to not make it over complex in this first video, which we already cover many different topics, and then let's leave it like this. Yeah, so this is our node, and we can have two constructors, by the way. The first constructor we will have as default, and this constructor needs parentheses, and here we can use brace initialization, which prevents those fields from having some garbage stored here. Yeah, so this will make sure that data will at least, like at the very beginning, will have the default value for int, which is 0, and default value for node, which is null pointer. Then we can create another constructor, which will come in handy later on, which will accept a single value. And that value we can put inside the data value. And we also have to then initialize explicitly next to null pointer, like this. Interesting. And since it's a single parameter, we mark it as explicit. Explicit, that's it. And so this is our interface. First things first, we have this internal node. What we store here, we now have to use it somewhere. We'll have the head of which type of node directly, no. Of node pointer, also no. Bad idea. Better, let's use unique pointer of node. Yeah. And this is one of our only two fields. The other one will be unsigned int called count, which will keep track of how many elements we have. Yeah. So each time we add an element, we increase it by 1. From start, we set it to 0. Then each time we remove it, we remove some element, we decrement it and decrease by 1. And so that's the idea behind the count. And head stores first null pointer when the list is empty, then the first element, and then where is the second element? It's not directly in the list. We have to access it through this next, and through the head itself. So let's say the list has 1,000 elements. The list itself, like the class, cannot directly access the 1,000 element. It has to go to the head. Inside the head, it has to go to the next. From the next, it has to go to the next. From the next, it has to go to the next, and so on and so forth. That's how it works. Okay, so that's the base of our interface. For now, we have those fields. But what is the class all about? Well, we have a mix of data and the methods that work with the data, modify it, read it, or do something like this. This is like the first pillar of object-oriented programming. So we have this encapsulation and abstraction, which, by the way, we also talked a little bit about. Separation through private and public is very good way of implementing abstraction. So we don't want to expose everything. Internal things stay internal. And together, data and the methods that work on the data. So now we are thinking about those operations, but before we even get to the modifying, we have to do the first thing, which is creating, as we have here. So we have constructor for the node. We also need constructor for the list. And it's a good thing to have 3 constructor default. Then the next one is copy. And we copy elements from a list, an object, an instance of a list that already exists. We create a new one through constructor, and from that other one we are copying the elements. But we are copying, meaning that after the new list gets initialized, both of them have the same elements, and the same in the sense that each box, each node stores the same value. But if I remove the element from the one of the lists, but not from the other, it only gets removed in this single place. So they are not referring to the same address in memory. This is a very important concept in programming and in philosophy. By the way, since a lot of confusion comes from misunderstanding of this copying by value and copying by reference. So here, which by the way is another subject. Here we are just talking about copy constructors. So here, const list reference to the other, and the other one, the other constructor will be move constructor. Here and now 2 ampersands, which is not reference to reference, but it's used for the move operation, and in this case move constructor other. And here some new keyword, no except, new in the sense that we haven't used it yet, and that is because those move constructor, and also it's useful to use it for move assignment operator. We'll get to it in a second. And those move constructors are preferred by some operations from standard library, for example pushback. And if you are not marking it as no except, you cannot use it there. Next thing is lists. What list? Destructor. So destructor we will leave empty. We will set it as default, the same as we did here when we will be defining it. And that is because we are not managing the memory, which is our only resource, directly. We will not need to free it by hand. Unique pointer is taking care of it. The next thing, if we already started assignment operators, so we can have list operator assignment and copy assignment. as well as what? Move assignment. We have two things. Okay, those are quite standard, and there are even some rules of 5 or something like that. I never remember, but basically you define them quite often together. And the next thing that we can define, if we have assignment, it's also useful to have to overload or to define the meaning for another operator, and that will be comparison operator. And comparison, by the way, can be marked as const, since we are not modifying anything here. That's those are the operators. Now maybe let's add append, modifying the data, adding new data into the list, and the data will be of type integer. That we cannot mark as const since we will be modifying the list. And the next thing is what else we want to have. We will want to have the get, and we're on index unsigned int index. This we can mark as constant, and look what we are exposing to the word int. So the word doesn't know anything about the nodes. The data that we store inside the nodes is the thing that we give outside. And by the way, also makes sense to make it here, have a private version of this that will return right now a row pointer. And we can call node add. And that is because here we are not taking the ownership. We are just picking into something that already exists and has its rightful owner. We don't want to take the ownership away. We don't want to create anything new. We just want to take a look into what's there. That is append and get. We can have also some helpers like empty. What else? Clear. I cannot write this unsigned. Unsigned in size, by the way. Next thing. What else? I'm thinking right now. Get empty clear. Size swap, maybe. That looks good. Yeah, so we have some interface. Now let's try to implement it. If we need anything more, we can add it always later. And let's start with those things. Yeah, I think that's already quite a lot. So first thing that we can define is a default constructor like this. And in the old ways, you would open the curly braces and do head equals null pointer. The next thing equals next thing, and so on and so forth. Yeah, but right now there is a newer way. In some version of C++, don't know exactly which one, maybe it was 14, maybe 17, maybe earlier. You can do it like this and put it even before the curly braces. Or we of course set the head to null pointer. Those are our two fields. Yeah, so this is our data. And those are all the ways to interact with it. Count is 0. And why null pointer and 0? That's because that's the default constructor. So user doesn't give us any additional information. He expects the list to be in its most raw empty form. Yeah. That's probably it. The next constructor is the copy constructor. Yeah? So we are copying the data from another list. And here, by the way, we can also copy this. Always forget about this. Yeah, so let's go back here. Here, some more complex things will happen. We will have to go one by one through the elements of which list of the other list, because our current list that we are constructing doesn't exist yet. And as we move through elements, we will be copying the values from those boxes, but leaving the boxes the way they are. Yeah, so we won't be changing anything or modifying anything. We already marked it as const. And we just take the reference. We want to see what's there and add the stuff to our list. So for node, we start from the head of the other, and we use get on unique pointer, which gives us the row pointer. And until the node is not equal to null pointer, which by the way can also be just checked like this, we will be moving it node equals to node next. Node next get. Like this. Checking, double checking. Looks correct to my eyes. I'm not yet sure. We'll check in a second. And then for each of this, we can append the data. So node data. Yeah, like this. But what does it mean to append the data? We haven't defined it yet, but we said that we want to have it. So let's define it right now. Let's define it right now. And the data. We will need to create a new node. std make unique. Of which type? Of type node. And we can use the default constructor, but we also have this constructor, explicit one, where we paste the value that comes from the outside, and we have now a node that stores the value. And so we have our box. Now, that's only part of the store. We need to go through all the existing boxes and place it at the end and connect it with the arrow. How do we do this? Well, we have to go one by one. Current starts at head get, and while current is valid and the next one is also valid, go one by one. Next, current, next. Then we simply move current equals to current next get. And now we move to the end of the list, but there are two cases. Current could be the last box, but current can also be empty, meaning that there was nothing in the list. Now we have two cases. First case, we just do current next equals to the new node. So this one was pointing to the null pointer, and now we place here the new node. New connection has been made. Other option is that head was already a null pointer. And then we place it like this. And by the way, this is a unique pointer. So how do we do it correctly? We do std move and std move. Okay. Looks like we have almost everything. We just need to increase the counter by 1. We have added one more element, and now we can proceed to the next constructor. Next one is the move constructor. So here we are copying, and the other was left the way it was. We just have copy of it in our new list. Now we are creating a new list and moving everything into this new list from the other. So other after that is invalid. Let's copy this here, and head will move from the other. Count we can just copy since it's a single number. Other, count, yeah? And after that you also have to reset it into other count equals 0. That's it. Looks like we have all the constructors. Now all the destructors, all of them, just a single destructor as usual. Shouldn't be more than one. And we simply put it to the default. Well, why? We already said it. We are not managing anything manually here. Everything is handled under the hood by the unique pointer. So that's it. Append. Now probably it's time to define the operators. Those are the operators. And let me put the curly braces everywhere. Let me separate them. And so which operators are we overloading? Assignment and comparison. For the assignment, the first thing that we can check is if the other, the one that we are comparing to our current, to this, and other, by the way, is passed by reference. So this is just a normal object. This is a pointer, so we have to get the address to compare them. Yeah? And if they are the same, then we simply return this, not the pointer, but the list, yeah, on the object. And we have to convert it like that through this operator. And for that to work, we have to define it here. Yeah, so let's move from here first here, and then we'll go back and fill it out. What happens here? Well, we have two lists. So we start both of them out of this node at their heads. So this at get, and the same for the other. This is not a pointer, so like this. And while both pointers point to the same data, so while this node is a valid pointer and other node is a valid pointer, we check first of all if they point to the same data, and data equals to other data, like this. If they are the same, if they are the same, it's okay. If they are not the same, then we return false. And then what we do, we move them to the next element. So this node equals this node next get this, and the same for the other node. Other node, and if at any point we move like box by box, any respective box from one list to another doesn't store the same value, then we return false. If by the end both of them reach the end, that means that the lists are the same. But if, for example, one of them had more elements after, then they are not the same. And so we check if both of them are invalid after we went out of the loop, if this node and not the other node. That's it. And so we have the comparison. Now we can also do this here. What else can we do? Here, copy assignment operator. Yeah, so we want to copy. Let's reuse the copy constructor that we already created here. So let's create a temporary list and copy the other here, and then swap with our current list, and then return the list. Yeah, but in order for this to work, now we have to define swap. What is this swap? And so for the swap to work, we will just use swap on our two fields. std swap other head and our head, and std swap other count and our count. So we swap both of them, and that should work. So we have swap as well. We have the copy assignment operator, now the move assignment operator. Here, I think we can just copy what we did here. But of course, we have to adjust the syntax like this. Bam, and left this. And now we can return. Not the pointer, but the reference, the object as reference. And that's it. So we have now the operators. Anything left? We have also append get. Get will be the next big thing. So for get to work, we can use the following. We can take advantage of the fact that we want to define this one, node add. Let's copy all of it, and we will define both of them simultaneously, and we will use it already in the net. Yeah? So we will get the node from node add on the index, and if node is not valid, then we simply throw. Don't take wrong. Oh, was using spaces for some time. Okay, yeah. So let's move this here. Yeah, now it looks better. STD out of range. There's some standard exception like this, and index range. We can paste a message or whatever. Would also theoretically say how big our list is, some other information, but let's leave it like this for now. And otherwise, we can return node data. That's it. But now how does this one work? Well, this one is a little bit more complicated. So note at index, we had to start again from the head. And while index is greater than 0, we will be moving the current one by one and decrementing the index until we reach the index that we want. Or, by the way, already we can check before all of this if index is greater than or equal to count, then we can already here return null point. That's it. Otherwise, we return here the current. Okay, we have almost everything. Just some helpers remain. Empty, clear, size. Then we can compile and see how many errors are here and discuss a little bit more what we can improve still today and in the next video. So bool empty. How do we check if it's empty? Well, we can just check if the head is valid. How can we clear it? Well, we can clear it by using reset on our unique pointer. It has reset function and setting the count to 0. And how can we implement the size? We just return the count. Well, those are easy. At the very end, some easy work. And that's it. Yeah, so now let's try to use it. We implement the list and try to, in some main function that will compile, use our list that we created here. Yeah, so we did a lot of work. Let's see if it compiles. Let's create a list like this, just an empty list, nothing else, and see if it compiles. I see already some error. Okay, just 2 errors. This one makes sense actually, the 71. Because this is internal type. Here. It looks like we compiled the wrong file. Let's try again. Okay, now process finished with exit code 0. Yeah, so it compiles. Let's now do some appends. So append 10, L append 5, L append minus 33. And after that, we can do std cout size of the list and the list L size sd end line and the elements. Yeah, so and do for I less than L size. We can increment I. Let's copy all of this and do the following. L on index I, close the brace, equals L get and index I. That's it. Okay, let's try this one. Yeah, so size of the list is 3, and those are the elements. On index 0 is 10, on index 1 is 5, on index 2 is minus 33. So now let's use our constructors. Let's create a copy. List copy of L and try to do the same. And copy. And it's the same, yeah? Also, our copy constructor seems to be working. And we can also check right away, are the lists the same? Have the comparison operator. Same. And here we can put copy equals to the L, and then aesthetic apply. And this is converted to 1. Yeah, so I think the bool is not overloaded for cout by default. Yeah, I'm not using cout that much nowadays, so I don't really remember how it works here, but seems to be working good so far. Now, what will happen if we do a move operation? So list and moved. We can move the copy and no, this we can by the way do it like this or like this std size of the list, copy. Yeah, and by the end we can also check the size of the list copy. And since it's supposed to be moved, and sorry, moved. Move like this. And size of the list copy is 0, since it was moved. So everything works as expected so far. We discussed a lot of different things, pillars of object-oriented programming. We discussed ownership, discussed the linked lists themselves compared to arrays. We show how to implement clean interfaces in C++. And of course, there are many more things that we can implement here. So there will be some new videos coming for linked lists, and then we will move to trees and graphs and some other interesting things as well.